Hello.
I am Eitan Sprejer. I am a student at ORT Argentina and I will be talking about the theory of special relativity by Albert Einstein. Do you remember when you were kids, going to the zoo and passing through the section of the seals that you said,
Wow, that's a very big seal.
But then you saw the mother and said,
Wow, that's really a very big seal.
Now, which of the two is truly big? The answer to this question is that the mother seal is big relative to the small seal, while the small seal is big relative to the child. Same happens with the movement. Wait.
I already knew this.
What's the new idea proposed by Einstein? Did it happen to you that while traveling in the underground you passed by the other train coming from the other side and the feeling was as if it had stopped moving while the other train moved? Most probably people on the other train had the same feeling.
I'm not moving, you are.
Is there a way to distinguish one movement from the other? Let's suppose another example. I take a taxi and my sister is driving the car behind me. She is in a hurry and drives faster than me. As she goes faster, she would see my car going backwards towards her. Okay. So it seems that it does depend on the person looking at it, so it could be said that the movement is relative to each observer.
What physics tells us is that
neither I nor my sister can do an experiment to distinguish if the car is standing still or is moving. But if my sister suddenly stops, this is a topic for another video. This is one of the two postulates formulated by Albert Einstein in the special relativity theory. Physics is the same in all inertial system, that is, at constant speed. It's the weekend and you're relaxed on the terrace and suddenly, it's a bird, it's a plane, no. It's Supergirl. Yes, Supergirl is flying and makes blowing wind. She sees the wind going to its normal speed. Obvious, right? And do you see the same? Not really. You see the wind speed going to its normal speed plus Supergirl speed. Now suppose that instead of wind, Supergirl throws a beam of light. Following the logic of the previous example, Supergirl would see the beam go at light speed while you'd see the beam move at its own speed plus Supergirl's speed, right? No. Both light beams would go at the same speed. This is the other postulate of Einstein's special relativity. The speed of light is the same for all observers. Now let's say a pigeon is inside the subway and going through the station flies upwards and falls downwards. The pigeon is going to go up and down for the people inside. But a person at the station would say he saw the pigeon pass in an inverted V path. As you can see, the pigeon travels a longer path as seen by an outside observer. Surely everyone would expect to see this, but this case was the one that led Einstein to think, what would happen if instead of a pigeon, a ray of light would do this? Would it happen the same? Now, what happens in this situation raised by Einstein is that seeing the beam, the viewer at the station perceives a trajectory longer than the one in the subway would, as would happen with the pigeon. But if the time it takes for the beam to travel the two distances is the same, the speed would change, which would violate the second rule of relativity. Therefore, to increase the distance, time to travel the distance should increase. So we can say that time passes slower on a moving object as seen by a stationary observer. So, to the observer at the subway station, time will pass slower in the subway. This phenomenon is called time dilation. But this is the problem. We spoke of relative movement, and according to that statement, for the observer on the subway he does not move while the rest of the world does, so the time goes by slower outside the subway. Then who is right? Here appears the twin paradox. This so-called paradox presents the situation of two twins, Zach and Cody. In this example, Zach is sent to space and Cody is left on Earth. Zach goes at a constant speed on the ship and travels 6 years straight, earns around and 6 more years traveling at the same speed to reach Earth. From Cody's perspective, he stood still, while Zach and his ship moved away from him. But from Zach's perspective, it was him and his ship that were static, while the universe was moving. So when Zach arrives to the Earth, who will be younger, Zach or Cody? A similar experiment was already done and Zach appeared to be younger than Cody. Einstein explains these results by saying that in times of takeoff, turning and landing, Zach experiences an acceleration force and no longer experiences the same laws of physics than Cody. Therefore, at that moment, Zach is the one that experiences time slower than Cody, as it is known that Zach is the one that is moving. But that's an issue for another video. Let us suppose we send a ship from Earth to a star traveling at a constant rate. From our perspective, the ship takes 10 years to reach the star. As time on the ship passes slower, the person inside the ship will experience less time until arrival at the star. But if speed is equal to distance over time, and speed is the same for the two observers, but time is higher on Earth, because more time passes, the distance should be longer on Earth. In the end it turns out it should. So the person on the ship would perceive a shorter distance between Earth and Alpha Centauri. This phenomenon is called length contraction. But what's the use of a theory that only makes a noticeable difference for speeds at which very possibly we will never get? The answer to this question is the GPS. The GPS is a system of spatial location which, using 4 satellites orbiting Earth from 20,200 kilometers above it, can calculate our spatio-temporal position. These satellites use atomic clocks, the most precise clocks of all, to accurately calculate our position. Now it is when it comes into play the theory of relativity. These satellites travel at 3,300 kilometers per hour, approximately on Earth. Although this speed is not even comparable to the speed of light, it is also not insignificant. Unless if it is to measure time with complete accuracy, since, without Einstein's theory, 3/millionths of a second would be delayed each second. That is 264 milliseconds every day, which would give an error of about 12 kilometers every day. This would mean many broken GPS